All right, here we go. Unit 2, Lesson 5, Tangent Line Approximations. We're going to learn one new technique today. It's an interesting application of derivatives, and otherwise we're just going to be strengthening our understanding of what a derivative is. So a lot of today is going to be review, but then the ends of each of these sections where we do tangent line approximations, I'm going to show you a technique that was one of the first applications of calculus and is a pretty nifty way to do some mental math. So we're going to get to tangent line approximations. First, we need a tangent line. And so the function we're going to use is this function g of x. G of x is 1/2 times x plus 2 squared minus 4. And this is going to lead us through the process. Part 1 says find g prime of -4. So find the derivative of this function at -4. Okay, I can do that. So we're going to take g of x. We're going to find the derivative using the power rule. We can't use the power rule yet because we're not in polynomial form. So the first thing I'm going to do is I'm going to square x plus 2. That's x plus 2 times x plus 2, which would be x squared plus 4x plus 4. If we did all of that math out, again, that's just this done out, minus 4. Distributing the 1/2, 1/2 x squared plus 2x plus 2 minus 4. Once we do this, now we have g of x in a polynomial form that we can deal with, 1/2 x squared plus 2x minus 2. That's a function we can take a derivative of using the power rule. G prime of x, so first we just find the general derivative using the power rule. Exponents multiplied by coefficients, 2 times 1/2 is 1. Exponent goes down by 1, so the derivative of 1/2 x squared is just x. The derivative of 2x is 2. So we have a derivative here. The slope of the tangent line at any point on this function is represented by x plus 2. So the slope of the tangent line, and I'm doing the explain what this represents part of this right now, the explain what it represents part, g prime of -4, which we can see here is going to be -2. That is the slope of the line tangent to g of x at x equals -4. And so the fact that we know it's actually 2, I can draw like a better tangent line than I usually draw. Down 2 over 1, down 2 over 1. I can draw some guiding points. To help myself here. Still tricky for me to do this. And, oh, this is going to be one of my best ones ever. All right, so there's our tangent line. It touches at -4, comma -2. And we're going to use that tangent line to approximate values of the actual function. So first we need the equation. We're already done with the really hard part here. If I ever ask you, as soon as you see in any problem, find the equation, literally the first thing, before I read anything rest of that problem, I'm writing down these two things. I'm writing down POT, point of tangency, and I'm writing down SOT, the slope of the tangent line. If you have a point and a slope, you plug it into point slope form, done. You've found the equation. And so we've got POT, SOT, slope of the tangent line at x equals -4. Well, we've already got that. The slope of the tangent line is the derivative. I told you, it's an important sentence. It's -2. The point of tangency, we can also just kind of look at. It's x equals -4, y equals -2. If we have a point and a slope, we can plug into slope or point slope form. Y minus y1 is the slope times x minus x1. To be clear, that is your x1, that is your y1. That's all x1 comma y1 means, is it means pick a specific point. So we plug in, we've got here y minus y1. So y minus -2 equals the slope, -2, times x minus x1, which is -4. Obviously, we've got some extra negatives going on here, so I'm going to clean this up a tiny bit. We have y plus 2 equals -2 times x plus 4. Nothing left. This is an equation of the line tangent. You could rewrite this in slope-intercept form, and you'd see a familiar equation to what you'd normally expect that line to look like. Now, here is where this gets fun and useful. It's one of the first applications that people ever use calculus for. Using the equation of the tangent line, using this purple equation, which again matches the red line, find the value of y when x equals negative 3.9. Then find the actual value at negative 3.9. I'm going to show you what this is getting at. What this is getting at is it's saying, I'm going to zoom in here, it's saying I want to know what g of negative 3.9 is. So something right to the right of negative 4. So I'm going to draw this line down here. I'm going to try and draw it as carefully as I can. Even this would be even closer. This is x equals negative 3.9. Those are almost the exact same thing. Do you see that? The red line and the actual function, when you are close to the tangent point, they are indistinguishable to the naked eye right now. And as you can see in a second, when we plug in, they're going to be almost indistinguishable. And it's going to be way easier to plug into the tangent line. So we're going to use the tangent line to approximate the actual value. First, I'll show you what the actual value is. And this is something that I've done ahead of time by using a calculator. It would be too hard to do in our heads. So if we have, right, if we have here, and I need to pull up because I've already done this. I want to make sure I have this ready. If I plug into my original equation, so I'll do this on the right here, then find g of negative 3.9. I'm actually going to do that first. G of negative 3.9 is 1/2 times x plus 2 squared minus 4. And so that's a lot to do. Even if you do clean up that parenthesis, you know, negative 1.9 squared, okay, 19 squared, I could do that. Like, it's a lot harder. I'm going to tell you that I looked this up in a calculator, and this is negative 2.195. So remember that number, negative 2.195. That is the actual value. If I zoom in all the way here and I look at the black line, the actual value there is negative 2.195. Let's see how close. Say we just say, the red line is good enough. Let's do just the red line, just the tangent line at negative 3.9. Y plus 2 equals negative 2 times negative 3.9 plus 4. Here's why the mental math is going to be a lot easier here. It's because this is going to be something we can do in our head. This becomes just negative 0.1. Or sorry, becomes positive 0.1, not negative 0.1. Negative 3.9 plus 4 is positive 0.1. And so we have y plus 2 is equal to negative 0.2. We subtract 2 from both sides. Y equals negative 2.2. Look at this. Compare these two values. For a lot of purposes, those are good enough. Negative 2.2 in a way that we could do in our head versus getting the actual value of negative 2.195. If you're actually sending someone to the moon, you want the negative 2.195 number. But for a lot of purposes, in a way that you could do this in your head, the negative 2.2 is just as good. And so to back this up, the key point here, zooming back out, is that if you have a tricky function and you are trying to find a weird value like negative 3.9, you can use the equation of the line tangent to the curve to make an approximation. As long as, like, notice this approximation, if we go too far, if we go out to like negative 2 and we compare those two values, yeah, that approximation is not going to be any good. So as long as it's close to the original point of tangency, you're going to have a good approximation, and it's something that's going to be worth doing. So that's the only real new piece from today, is that tangent line approximation, and Delta Math will get you some basic at that.